So we're going to have a chat. And we're still talking about gas chromatography, but the problem is that we're focused on another side of the instrument. And the side that we're going to be focused on is on the front end and not the back end. And there's actually two attachments that we're going to discuss. This one, which we call Headspace, and then another one, which we call Purge and Trap. So as in the Purge and Trap videos, when you get to that point, what you're going to see me draw is basically the GC box. So this is where all the magic happens, and this is where we've been talking about. The injector site, the column, the detector, the computer system, the software, the chromatogram. All of the data is getting fed through the GC system. And off here to the right-hand side, I'm going to draw a separate box, and this box is going to represent my detector. We talked about a couple of different detectors, TCD, FID, mass spec. Those tend to be the more common ones that you'll see out in a laboratory somewhere. And we talked about those differences. But really what we're focused on now is what changes on the front end of this system. And we can have various attachments. So if I was in the kitchen and I bought a nice new swanky KitchenAid mixer, that mixer can do more than just mix cake batter, right? So I would purchase these attachments and I would attach it to that cake mixer, and then all of a sudden I could have a meat grinder instead of a batter mixer. So my usage of that instrument somewhat changes. Well, what we're focused on here is called Headspace. And there's some opportunities that you might see out there, especially in an environmental laboratory, that will look at Headspace and use it as the most common way that they perform GC studies. All right, so let's talk about Headspace and really what it means. All right, so let's say that we've got a vial or a container, and I've got a lid on it. Could be a screw top lid, maybe with one of those pieces of rubber septa in the middle so it can get punctured. But in this container, I have a liquid solution. All right, if this liquid solution was just simply an organic molecule, then, I'm A-okay. My GC system is going to be able to accept this compound, and it can analyze this compound, and I can get data from the compound. The problem is that I just have to make sure that I don't inject too much. So if anything, what happens here in this case is that I'm going to have to lower the concentration down. But the GC system is able to handle the sample. It can process the data, and I don't really see any kind of major problems with that type of analysis. So maybe one of the things that you've done here so far is an analysis of banana oil. You've made your own banana oil. You've went through the process of synthesizing it, making it, and running it on the GC system for purity. Or maybe one of the things that you've done up to this point is a solvent mixture lab. And the solvent mix was basically acetone and maybe some heptane and maybe some toluene, depending on what we gave you. All of those are typically organic, right? Acetone's organic, heptane's organic, toluene's organic, banana oil is isopentyl acetate. That is an organic compound. All of those organic compounds, right there, there's the magic word, can be analyzed on a GC without a problem. It's just an amount. You don't want to oversaturate the system. So you're going to have to be really careful with how much you inject in. And then depending on that amount, you also want to pick the right split ratio to make sure that it can be smaller going into the instrument, because you still could have overloaded it. Well, here's the issue. Not everything in a laboratory is organic. Go figure, right? So what I mean by that is that there could be a chance at some point in time that somebody will bring me an aqueous solution. All right. That aqueous solution, I scribbled it. I probably spelled it wrong too at the same time, but I'm not going to take the time and correct it. All right, so with that aqueous solution, that means there's water involved. And then in that water, we might want to look at various compounds that are inside of there. And these compounds maybe are organic ones. So these are very suitable for a GC system. They're organic, they're carbon-based mainly, they probably are volatile or semi-volatile, they have low molecular weights, they have low boiling points, they are perfect candidates for the GC system. However, they are mixed in with this water. They're mixed in an aqueous environment. And we've already talked about the problem with water. We said this is a no-no when it concerns the GC system. Water is a destructive force. It can do damage to your inlets. It can do damage to your columns and your column stationary phase. It can also do damage to the detectors. And you want, as much as possible, to prevent the incorporation of water into the GC systems. So here we have a problem. We have a sample that's aqueous based. And we have things that we want to measure on the inside of that water sample, which are organic based. And those are perfect candidates for the GC. The water is not. So we need to get rid of the solvent. So you're probably thinking, okay, well, that's not a big deal, right? Maybe what we can do is that we can take this vial and we can put it on a hot plate and we can heat this stuff up. So we can evaporate off the water and we'll have the organic compounds that are left behind. Nah, that's wrong. You can't really do that. And the reason is because those organics in that water sample, they actually might have a lower boiling point than water. So if they have a lower boiling point than 100 degrees, then these are going to evaporate off first. Your water's still going to be left behind here in the container, and it still might have some volatile organics that you maybe could have measured after the water dissipates and goes away. But the problem is that you've lost everything in the beginning. So this is not going to work for me. I can't really just heat the sample up, drive the water off, and then inject what's left over. Doesn't make any sense. I'm losing product. Okay, so let me erase this diagram. That option's not going to work for us. So we have another option. What if I take this container with the lid and it has some sample in it, and what if I just let it sit? Right? I don't do anything to it at all. So here's the water. And if I just let it sit, some of these compounds that I want to measure on the inside of that water sample, they could be volatile. They hate the water. So if they can find an escapage point, then they will leave that water sample and they could start to crowd up in the top part of that container. The top part of that container would be right up here, in basically the air. No water, no solvent up there. It's just air. All right, this is the term that we use for headspace. So when we talk about injecting headspace onto the instrument, what we are referring to is basically the area above the liquid sample that some of these components maybe have evaporated up into. And they're ready. They're separate from the water. So they are ready to be injected on the GC without a problem. All right, so that's great news, right? We can take advantage of that, and we don't really have to do anything to it. So now the question that you should ask yourself is, okay, well, what if there's other components down into this water sample too? And let's say that these other components have boiling points. What if those boiling points were not at room temperature? right? I mean, would those still stay in the liquid solution? And the answer to that question is yeah, they could, right? If you were doing all of this stuff at room temperature and that boiling point for that organic is, let's say, 80 degrees, well, it's going to have a chance to not turn into a vapor. And if it can't turn into a vapor, it can't go up into the headspace above, at least not a lot of it, right? So there's an issue here, and you might be actively thinking now, and you'll be like, well, that's kind of easy to take care of. Let's put this sucker on a hot plate, and let's turn up the heat, and maybe what I can do is warm this container up. And if I can warm this container up, I could maybe help drive off some of these components that might be a little bit stubborn. This is the field of headspace. But guess what? It used to be manual. Not anymore. It's now an automated process. So when we talk about a headspace analyzer, what we are referring to is an instrument that can kind of do this idea for you. That's its whole purpose. I don't want to be over at a hot plate heating closed containers up, trying to keep everything consistent as far as the heating goes, trying to keep everything consistent as far as the timing goes. It's going to drive me crazy. So the headspace analysis will do it. I literally tell it the temperature that I want to heat it. I literally tell it for how long I want it to be heated for. And then the auto sampler unit in the headspace will puncture the container, suck up the headspace into the auto injector needle, and it will deliver that over to my GC system. It's as simple as that, folks. That's all there is to it. All right, so if you've taken our forensic chemistry course, you probably experienced a blood alcohol content lab. And the blood alcohol content lab used the Headspace GCTCD unit or FID unit. We actually have both of these detectors on our Headspace system. And that's exactly what you did here. But you were focused on ethanol. And ethanol has a lower boiling point than water. But you were driving the ethanol up and out of those samples, and that ethanol was getting delivered to the GC system, and then that's where it was getting picked up and measured. The same way what happened to the blood sample. The blood samples that we probably injected at that time, those are very complicated aqueous-based samples. You can't just inject blood onto a GC. You got to drive off those organics. Those organics have to be transported over to the GC in some form or fashion, and then they can be measured, and then they can be detected. All right, so let's take a look at our GC Headspace system. What do we actually have in our laboratory? So it's going to look something similar to this, almost identical actually. This is an Agilent system here, and this Agilent system is the GC box. And of course, this is the software and computer that operates the entire system as a whole. This GC box is getting fed, and it's getting fed with those organics. And those organics are coming from a Headspace unit. And the Headspace unit is right over here to the left. It's just another simple box. Ours is from Agilent, and our model number is G1888, I believe. And this model number basically has a tray up here at the very top, and you can see some vials that are loaded in it right now. And then you see this hood. All right, so what happens is that the vials are loaded up by you, and those vials are probably aqueous in nature. And this auto sampler will take the vial, and it will basically suck one of the vials up underneath the hood. So it transfers it up in the oven. And this is going to be where the sample gets heated. So up underneath this kind of tray, the sample vial will go into, and it kind of gets lowered down a little bit. And then this sample gets heated for a certain amount of time at a temperature that you've selected. And then once that heat process is over, there is a auto-injector needle that will then pierce the septum of the container, and then it will transfer that sample over in the GC unit. And you can kind of see that connector tube right here that comes up and over. The end of this injector tube is actually attached to the injector port of the GC system. That's where you would be manually injecting samples anyway. So this thing is made to attach at that injector port, so that way you can easily take this off if you do not want to use the Headspace system, and you can convert this back over to a normal auto injector or a manual injection if that's what you want to do with it. So it's very user-friendly. It's very easy as far as attaching it to the inlet of the GC system. And it gives you some flexibility in what you want to do with the GC as a whole, right? So again, this is my KitchenAid mixer right here. And the Headspace unit would be another paddle or another attachment that I would attach to that mixer to maybe change its purpose or to do something a little bit different with it. The box here in the middle, who knows really what that box is? It's probably another type of detector. It could be maybe a hydrogen generator, but honestly, it's probably another type of detector that's connected to this GC box. All right. Okay, so there's the story with the Headspace. So here's a better view of that instrument, just the Headspace unit by itself, and it gives you a better picture of the auto sampler tray that's up here at the very top that kind of winds around, and then it can be lowered into the heating chamber that sits down here below. This whole lid up here at the very top, this thing will open up, and that way you can kind of take a look at the internals of the oven site, and then you just kind of lower it back down like a car hood, and you just kind of attach it and secure it. That way this thing can hold at temperature and keep that temperature steady for you over a course of time. As far as the user interface goes here, the software really doesn't connect to this, at least the model that we have. This is more of a user input. So you would tell basically the auto sampler here how many samples you have and what vial numbers you have went up to. So I've went through maybe vial 1 through 11. And then it will know that it will take vial 1 through 11, and it will begin to process those samples for you and deliver it over to the GC system. So in the software and in the computer, you're still filling out the batch table for the GC system. So that is where you would put the file names, the method names, the sample names, put them in the order that you're running them. GC system software will save that information for you just like normal. So you pretend like this is a normal injection type. However, with the Headspace side, it doesn't really care about any of that, right? The only thing its job is to process a sample and deliver it to the GC. So the GC will be waiting, and it will be waiting on a sample, and this Headspace unit will do what it needs to do, heat, keep it there for a long period of time, and then inject it over. When this gives the relay to the GC system at that point will then kick in and say, okay, we've got a sample, now we're running it. And that is line number 1 on your auto sampler table on the software. Okay? Then this heating unit will go ahead and process sample number 2. It will configure the time. It knows basically the run time. It knows everything that you're doing as far as sample processing goes because you've entered that in. And it will go ahead and start sample number 2 and start processing it the proper way when it is ready for that moment in time. And then after that, it will send that second sample over. The GC kicks in and says, okay, I've got a sample now. This is number 2. And then it moves on to the second line item in your auto sampler batch. So this is not software controlled mainly, at least the way that ours is set up, and some of the major ones in a laboratory are set up, unless they have a newer model. All of these are inputted through the keypad. Temperatures basically get keyed in like a phone number. Your time intervals get keyed in like a phone number. No big deal. You type in the numbers and you hit the enter button. That's all that you've got to do with the Headspace unit. Here's the back end of that Headspace unit. What you're seeing is basically a fan that helps kind of cool everything down and get it ready to be heated all over again with a sample. Back here on the back are the power cords and the hookups to basically the GC instrument, so that way it can start relaying the messages to the GC that it's ready to inject a sample on it. And then finally, what I like about this picture, this is the hose that basically transfers your sample that's been prepared over to the GC. And if you take a look here at the very end, that is your injection port. So this basically goes down into the injection port of the GC and it locks in place and you secure it. Again, if you don't want to use the Headspace box, no big deal. You take this back out and then you can put your auto injector back on it, or you can manually inject onto the machine after that. So it does not need this to work, but it's using this almost like an auto sampler preparation step that can start feeding the GC sample after sample after sample. If we open up the top of the box, I told you it opens up like a car hood, right? So here's the digital kind of readout, and here's the keypad on the front of the machine. You see that kind of there at the bottom. The only thing you got to do is push the buttons on the side, and this thing pops open, and you can kind of see the valve entry ports here. Okay, so that is where your container would basically be lowered into this oven, and this oven is insulated just like the GC door is and the oven to the GC, so that way it can help control the temperature a little bit better for you. There's multiple vials that are basically here up underneath this tray because it knows that it can be processing one sample and it can start bringing the second sample into the tray and into that area and begin processing that one as well. That saves you a little bit of what we would call hold-up time, right? So for instance, let's say that we tell this machine, I want you to heat the sample for 10 minutes. And on the GC box, the runtime is 5 minutes. That's it. Then it's over. Okay, well, if this went normal, what would happen is that it would lower sample in, heat it for 10 minutes, take the sample, transfer it over to the GC, and in 5 minutes' time, the GC would now be finished. Well, you don't want a delay, meaning that you don't want the GC to be finished, and then this one takes its second sample and just begins the heating time. If so, that's going to expand your run times another 10 minutes because you've told this instrument to heat the sample for 10 minutes. So this thing is smart enough to know, listen, if the run time is 5 minutes, what I could do is bring another sample in. I could go ahead and start this heating process. And as this sample is heating, I get a head start. And by the time this second sample is finished, the GC box will be finished with its run, and it will be automatically ready for the sample because now I can send that sample directly to it. There's no more wait time in the middle of this mess. So that is why these temperature parameters and these time parameters are very important for you to enter in, because it can be smart enough to be processing other samples in preparation of the next runs that will happen on the GC instrument. So one of the documents that you're going to see with the Headspace folder and the Headspace discussion is this from ResTech. And it's called A Technical Guide for Static Headspace Using GC. So it's going to go through a little bit of the theory and background about the Headspace system and the purpose of it and why someone would want to use it and why it's pretty important. So some of the questions that you're going to see from the assignments are going to come from this document. And you want to go through and you want to kind of just read and skim through this paper or information booklet. It's about 20 pages long. It's full color. So depending on the speed of your internet connection, you might see a slower or larger view or slower download time, but you'll eventually get there. All right. So here on the very first page, it says static headspace gas chromatography is a technique used for the concentration and analysis of a VOC. The technique is relatively simple and can provide sensitivity similar to dynamic purge and trap analysis. Now, notice it says similar. It doesn't say the same. We have a purge and trap system as well. The purge and trap system's a little different, though. We would use it in a different scenario, and we'll talk about that because we'll have another folder on the purge and trap system. But they are very common. One is preferred over the other one in a certain case, and we'll talk about that when we discuss purge and trap. The popularity of the technique has grown, and it looks like more and more people are beginning to use it. More and more labs typically have this as a pretty much common instrument or attachment now at their disposal whenever they need it. And it says it's gained worldwide acceptance for the analysis of alcohols in blood and residual solvents in pharmaceutical products. So if I go out to a pharmaceutical company and they're basically making blends or testing of different drugs, and they've used solvents in order to do that, and let's say they drive those solvents off, they want to make sure that none of those solvents or minimal amount as much as possible is given to a consumer. So those products are tested to see if they could pick up any of those traces of solvent maybe that shouldn't be there before they release the product out. You can go through and take a look at this, read it on your own, but you're going to see a diagram here of a vial, and it's basically kind of like what we've drawn before. They're talking about a gas phase up here at the very top, and then they talk about the sample phase that's down here at the bottom. The gas phase is what they refer to as the headspace, and this is the area where all of those vapors are going to start to accumulate. And then the sample phase is down here at the bottom. And this sample is basically the solvent, traditionally aqueous solvent that I don't want to inject into the system, with maybe some things that I do want to inject into the system. So this will allow me a separation technique that I can then just inject the gas phase only onto the GC system. Another page in the manual is going to basically talk about shaking or vibrating the vial. Shaking and vibrating is actually a setting that you can put on the Headspace system. So not only will it take the vial and put it into the oven and begins to heat it up, but there is a small vibrator or shaker on the inside as well. And you can turn this on or you can turn it off. And it really is just a user interface or an SOP method setting that you have to ensure that is set properly before you start the analysis. But some people believe that if you shake the vial back and forth slightly or vibrate the vial slightly, that you can kind of jiggle out some of these volatile organics a little bit better. So it helps the molecule to release out of that sample phase and helps it go into the headspace or the gas phase, and that is where it's going to be pulled out and injected into the GC system. Our unit has this option. We can turn this off and on as we need, and quite honestly, the methods that we use on it do not require the shaking method. So we normally leave it off, but we do have that capability if we need it. On this page of the information brochure, you're going to see Headspace applications. And the very first one that they start with is blood alcohol analysis, or BAC. The blood alcohol analysis, what I want you to focus on here, and maybe I can zoom this up a little bit so you can see it a little better, is going to be figure number 12. This is your typical method that you might see with a GC system, and they're showing you a normal chromatogram with all of these samples. This is traditionally what it would look like. But down here below, you're going to see a little information about the Headspace system. So it says a dual column analysis using a 2-hole ferrule, and it says a 1 milliliter Headspace sample of a blood alcohol mix. So the oven is set at 40 degrees and it's isothermal. The injection temperature of the GC system's at 200 degrees. The carrier gas is helium. The sample equilibration time is 70 degrees. So that means in the GC or the Headspace unit, I probably want to heat that up to 70 degrees at least, right? Because that's what my method is telling me. Then it says sample equilibration time for 15 minutes. So I'm going to heat it at 70, and I'm going to keep it at 70 for 15 minutes before the GC even sees it. The vial pressure is set at 30 psi. So we're pressurizing these systems, and we're making sure that if we can increase the pressure, then our boiling points begin to change, and we don't have to heat things up as hot anymore. So it kind of helps out those boiling points a little bit, and everything can get a little bit lower because of that. The vial pressurization time is 0.15 minute. So how long do I get it there, or does it take to get there? And then the vial sampling time is 0.01 minute. So that's literally a quick puncture the vial, suck out the top, and transfer it over to the GC system. The transfer line temperature is set at 200. When we suck things out of there, we don't want them to condense down in the transfer line. So this thing has to be heated too. That's why that tube is pretty thick. You saw that in the previous pictures. It was a pretty thick wide diameter tube, but that's because it is very well insulated and there is a heating coil that goes around it. The injection port sleeve and the split flow. So all of those settings are going to be in the methods for us. We just kind of know which ones go with the Headspace now, and it's all of these sample vial times, the temperature of the vial, how long do we keep the vial there, and then the pressure. How high of a pressure do we need to go with those units? So the next thing that I want to talk to you about is the vial itself. The Headspace system, there's kind of a special vial that you need to use. I mean, this is something that you've really not seen before in the program up until now, but it is a Headspace vial. And the Headspace vial is basically a piece of glass, and there's typically like a lip here on the very top of it. And the lip is made so that way we can put a cap over it. And this cap is going to have to be crimped because, listen, we're heating this stuff up and we're increasing the pressure of the vial. So these lids have to be super tight. Like a screw-on lid is not going to work out for us too well. So we have to make that next step, and we have to ensure that these things can pressurize and that these are not going to blow their tops, literally, because if the vial goes off, the lid of the vial goes off, then all of our sample goes off with it. So what you're going to see here in this video is a vial crimper. And what this guy is doing is he's going to show you how to basically crimp the lid on one of the vials in a laboratory. So up here at the very top, you're going to see the crimper, and the crimper is here in the very top of the video. And then we've got a vial or a container that your sample would be going down into. And then this kind of lid, you might not see one of these lids in our lab, but this is just one option that's out there. So we see a piece of rubber stopper that goes into the middle. This is kind of like your septum on a GC system, kind of the same type of material. The lid goes on that piece of rubber. That lid can be punctured by the auto sampler needle, and then the crimper goes on to the top, and you just pull the lever and it crimps the lid in place. I mean, it's as easy as that, people. It doesn't really get any more difficult than that. So now you have a completely crimped lid at the top that can withstand some high temperatures and some high pressures on the inside. You have to prep all of your samples up in those containers first. Those containers go into the auto sampler, and those typically do not get reused. That is it, right? So they're one-time use, and you throw them away. I will also post another video made by Agilent into this folder. And this is what you'll see in that video. It's a guy that basically has some vials that he's filled with some liquids, and he needs to crimp the tops on these vials. So they're going to show you the way Agilent does it. They're going to show you some different options that might be out there. And there's a manual crimper, which is what you just saw. And there's also an automated crimper. You know, doing these over and over, let's say you had 100 sample vials to do. Crimping 100 of these is going to work out your wrist quite a bit. So is there something that we can make our life a little bit easier with in the laboratory? And the answer is yes. And that's what this guy's going to show you in that video. So make sure that you watch it. Make sure that you take a look at it and kind of understand what he's doing. I think that you'll like this kind of crimper much better. But guess what? We don't have one of these. We have a manual one, and that's okay because we don't do a lot of sample processing anyway like they would do in a normal laboratory. So finally, some things that I want to leave you with in this video. There's others, of course, that complement what you've just heard from me. But the Headspace system. I've talked about this Headspace attachment, but I want you to understand that this can also be done manually, right? It is a very or much more labor-intensive process. You're going to have to be really particular with the times, really particular with the temperatures. You can take a Hamilton syringe, which is the injection syringe used on a GC, suck up the headspace in the vial on your own, make sure that you have the proper amount, inject that amount, which is just basically air, inside of the GC system and let it analyze. So you can do this on your own. You do not need an attachment, but if you have an attachment, it makes your data processing and your sample injection much better and much more reliable than if I just turn someone loose on a whim and say, here's a syringe, go at it. So for that reason, Headspace automation has become very popular in a laboratory. I also want to say that we've talked about this sample. And this sample, I said, listen, you've got some components in here that you want to measure. It's very good if those components are kind of in a higher concentration. So this Headspace really should not be used for trace amounts. That's really the purpose of the purge and trap, and that's what you're going to learn about in the next folder and then in the next couple of videos that you'll watch. But the Headspace typically works out a little bit better if the compound is present, if the compound is present in a large amount where you don't need any kind of specialized detector to get that low. And the reason is because you're relying basically on the compound to evaporate. You want it to go into the Headspace, which is up here at the top, and the less of that you have in the sample, the less of it that you're going to get up into the Headspace, right? And you're going to get to a point where that amount, no matter how much you've heated it up, that amount cannot be seen by the detector if it's there really super low in the beginning in the first place, right? So the purge and trap will kind of allow us to do that a little bit. No matter how much I heat this up, though, keep in mind equilibrium is going to be achieved, meaning that I can heat this sucker up more and more and more and more. But just because I heat it up more and more does not drive off every single thing in that sample. Some of it's going to stay behind. And it's all basically like diffusion, people, right? We said that things travel from a high concentration to a low concentration. And that's why Headspace works. So a higher concentration is in the solution, and it's going to travel to a lower concentration up above. There's going to be a certain point, though, where the amount that's up above is going to be almost the same as what's down below. And no matter if I heat, it's going to be very difficult for me to drive off all of these compounds into that vapor that sits up above. So, because of that, we need maybe another option at our disposal, and that is the purge and trap system that you'll learn about next. But that's one of the problems with Headspace, right? You can't drive everything off. You can drive it off proportionally as long as everything stays consistent. You can make calibration curves. You can do data analysis without a problem because it's all treated the same way. But if you're thinking that all of this is leaving the sample, you're wrong, because it's not. Some of it's staying behind in that liquid solution, and it will never go to the headspace that sits up above. However, the more of it that's in the liquid, the more of it that will be up here in the headspace unit. And that's why the data analysis begins to work. Okay, so take a look at some of these other videos about headspace. You'll go through, maybe I've got a couple that kind of show the headspace manually, the headspace working on its own. You get the drift. And then good luck on the assignment. It will all focus on the headspace system, and that's it. So take some good notes, review that document, and I think that you'll be okay.